everyone, and welcome to today's Explainer. Today, we're exploring a foundational concept that literally shapes how you see the entire universe around you: the reflection of light. If you're a fan of a structured, no-nonsense breakdown of how physical phenomena actually work, well, you're in exactly the right place. Let's break down the principles of ray optics step by step so you can walk away with a crystal clear understanding of exactly how light behaves. Okay, let's dive into this. I want you to take a quick glance around the room you're sitting in right now. Really, look around. Everything you see, the desk, the walls, that cup of coffee, it's all visible to you because of an invisible, high-speed physical interaction happening billions of times per second. So, how do those light waves actually interact with everyday objects? Well, to understand that, we need to understand the fundamental physics of the bounce. Let's kick things off with Section 1, the optics of reflection. Before we get into the complex geometry of angles and surfaces, we've got to establish a baseline. At its absolute core, the reflection of light is a fundamental phenomenon in optics, where light waves encounter a surface and bounce back. I know, it sounds incredibly simple, right? But this concept of the bounce is the absolute bedrock of everything we're about to discuss today. Think of it kind of like throwing a tennis ball against a brick wall, but, happening with microscopic waves of electromagnetic energy. The light travels, it hits an obstacle, a surface, and instead of just passing through it or disappearing completely, it gets rejected. It bounces back. That bounce is the pure essence of reflection.
Moving right along to Section 2, crossing the boundary.
So, we know light bounces, but what actually triggers that bounce in the first place? It requires a very, very specific condition. To quote our source material directly, this process occurs when light waves strike a boundary between two different materials. Notice that key word there, boundary. Reflection is fundamentally an interaction between two distinct things. The light has to be traveling through one material, and then, boom, suddenly it hits the frontier of a completely new material. It's at that exact meeting point, that boundary line between material A and material B, where the magic of reflection is literally forced to happen. So you might be wondering, what is the light traveling through before it hits that boundary? More often than not, it's originating in one of two incredibly common mediums: air or a vacuum. Just think about sunlight traveling millions of miles through the empty vacuum of space, or a regular old ceiling bulb shining through the air in your living room. This is what we call the original medium. The light is just happily cruising along through the air or the vacuum completely undisturbed until it hits a boundary. Now, what's really interesting about this interaction is how we can break it down into three distinct steps. Step 1, the light waves travel through their original medium, like we just talked about, air or vacuum. Step 2, the waves strike a boundary of a completely new material. Could be glass, could be wood, water, you name it. And finally, Step 3, some, or maybe even all, of those light waves are redirected back into that original medium. They interact with the surface, and they're sent right back the way they came. And this three-step process, it's happening everywhere around you, constantly. All right, let's look at Section 3, the angle of incidence. So the crucial point is, when that light is redirected back into the original medium, is it just total chaos? Does it scatter wildly in random directions? Absolutely not. Physics is elegant, and it follows strict rules. When light is redirected, it maintains its angle of incidence relative to the surface normal. Let's unpack that for a second, because it is literally the core mathematical concept of ray optics. Imagine an invisible line standing perfectly straight up, exactly perpendicular to the surface the light is hitting. That imaginary straight line is called the surface normal. When the incoming light wave hits the surface, it comes in at a specific angle compared to that straight line. That is your angle of incidence. And the golden rule of reflection dictates that when the light bounces away, it will maintain that exact same angle on the other side of the normal line. If it comes in at a sharp angle, it bounces off at a sharp angle. It's a perfect, predictable, geometric mirror image of its arrival. Pretty cool, right? Let's bring this home with Section 4, smooth versus rough surfaces. And this brilliantly illustrates how we apply this abstract math and geometry to the physical world you can actually touch and see. While the mathematical rule of the angle of incidence always applies, the visual result looks very different depending on the physical terrain of the boundary itself. First up, you have smooth surfaces, like a mirror. Because a mirror is microscopically flat, all the parallel light waves hit it and bounce off perfectly together in the exact same direction, maintaining their angles perfectly in sync. That's exactly why you see a crisp, clear reflection of your own face. But then you have rough surfaces, which, let's be real, is what most everyday objects are. Think of a painted wall, a piece of paper, or the shirt you're wearing. On a microscopic level, these surfaces are super bumpy and jagged. So while every individual ray of light is absolutely still obeying the rules and maintaining its angle of incidence relative to the tiny microscopic bump it just hit, all those tiny bumps are facing completely different directions. Because of that, the light waves are redirected back in slightly different, scattered directions. It's still reflection, it's just a scattered reflection, which is exactly why you can see the color and shape of your wall, but you don't see a perfect reflection of yourself standing in front of it. Which brings us to our final thought for today's explainer. We have traced the incredible journey of light. We've watched it travel through an original medium, strike a boundary, follow the strict geometric rules of the angle of incidence, and then scatter or reflect perfectly depending on just how smooth that surface really is. So I want to leave you with this question. Next time you look around your room, can you picture those invisible angles of light? Can you imagine the millions of rays hitting the smooth glass of your window and the rough fabric of your chair, bouncing perfectly according to the laws of physics, just to bring the world into your vision? It's a truly fascinating way to look at the world. Thank you so much for hanging out and learning with us today. And keep exploring that incredible